I'm glad we got a straight cough on the broadcast. Okay.
So are you using university property, or are you maintaining them as a course that you're developing?
I'm just putting the courses, I'm just live streaming it to YouTube, so okay. I guess anybody can watch them. But. All right, well, I guess we can get started. So this is going to be our last lecture on ray tracing and global illumination. So we're going to kind of wrap some of this up today. So we'll just review a few items. So what classical ray tracing, global illumination, the three different techniques we looked at, path tracing, radiosity, and PRT, pre-computed radiance transfer, or they're often called irradiance volumes. So search for both of them, get both techniques. Talk about real-time ray tracing and the 6 kind of elements that go along with that, and how to kind of approach learning how to do ray tracing, which is part of the homework, and continue our discussion on ray marching and different transformations. Okay, so I think the next homework's due this weekend. So that's the first homework due is this weekend. So ray tracing. So the idea here is we have a camera, we have light sources, we have objects, we have a screen, and we'd like to be able to sample the image, which we would call the image viewing plane, by shooting rays either from the light source or the camera. So we call it backwards ray tracing. If we go from the camera, we call it forwards ray tracing. We start from the light source. And the problem with that though is you tend to get, you get full coverage with the camera, and you can get mixed results if you start with the light source, because most of those rays don't end up on the screen. So, but we can use path tracing as a way to kind of put all those paths together. So first problem we have to figure out, how do you get rays to go through the pixel? And so we'll be talking a little bit about that today. And then to kind of start the discussion, we have classical ray tracing. So this was started with Turner-Whitted, 1979. And the idea here is it solves 3 problems: shadows, reflections, and refraction, which were each their own subproblem with rasterization. However, ray tracing would still be way too slow, even for the following 2 decades, essentially. So, and the reason for that is that it tends to have exponential growth per pixel, because for every object that you trace, then you have to figure out, okay, reflection rays, refraction rays, shadow rays. And so this doesn't have very good asymptotics for performance. So it's one of the reasons why in the 70s, when nobody did ray tracing, because yeah, they knew that's how you solved the technical problems of each one of them. But the main thing is, while you just spend so much time doing it, you never get an image. So after Turner-Whitted said, let's just do everything, we see some improvements with the introduction of the rendering equation from Gajia and distributed ray tracing with Cook and a few others in the mid-80s. And so one of them is, let's approach ray tracing using Monte Carlo methods from physics. And Cook was working on how do you get better images, right, that have more interesting stuff associated with them. Like, so they said, let's distribute rays over time and space. And that way we solve problems like translucency, motion blur, depth of field, anti-aliasing, glossy surfaces, and penumbra for like shadows. And these would be pretty de facto ways of doing ray tracing up into the 90s, when we got some new approaches, namely like bidirectional path tracing, METROPOLIS light transport, and a few others. But basically, they get your path tracing results much quicker by multiple important samplings. That's what I was thinking of. They do a better job of figuring out, of solving some of the problems with path tracing. You know, you get all these fireflies, in noisy images, and how can we improve that? So I have a link here to the path tracing renderer we looked at a little while ago, but these are some classic scenes from a few of these papers, including the 1984 one from Cook and others. So it's kind of tongue-in-cheek, right? Because 1984, and you have the book, and so anyways, all the problems it's solving is pretty cool. So we talked about path tracing, and so over here in this image, you can see some of the problems you get with path tracing right off the bat. Namely, it's fireflies and noisy images. Fireflies are basically hot spots in your image, and the noise is just, you don't have enough samples to determine what the pixel ought to be. So this is more or less what real-time path tracing looks like today. And so much of the work that's happening right now is noise reduction, or how can you get rid of the noise by using as much information. So this actually gives you enough information to reconstruct an image that's pretty close to the ground truth. You just have to kind of understand those relationships. So bidirectional path tracing is basically combines forward ray tracing and backwards ray tracing. So we can trace rays from the lights into the scene. We can trace rays from the camera into the scene. And at some point, at some ray depth, we can connect the two and figure out via the BRDF how much light from this light source then is contributing to this surface over here. And we'd have to use hemispherical integration though to get a good sampling for each surface. So proofs in the pudding. So if we compare same computation time, we can see that bidirectional path tracing immediately has way better results than just pure path tracing. You get the same result if you let the path tracer work for longer, but for the time constraint, when you can at least guarantee the results not any more biased than the other one, you might as well go with this other approach. Metropolis path tracing is particularly good for certain kinds of problems like caustics, but we also talked, if we look at and analyze these two images together, that yes, you get more noise with bidirectional path tracing for caustic areas, but you get more noise with Metropolis in general. And that's because there is no like magic function that can say if you mutate the light paths, then this will automatically get you a better result. And so because of that, Metropolis can guess wrong. And so you have to kind of, this one takes more effort to kind of understand and play with, but it's certainly an option, especially if you're dealing with caustics. We talked about importance sampling. Importance sampling is basically how can you statistically allow the rays to travel in a more convenient direction. So if we were talking about the BRDF, you could use the Fresnel function. So if the Fresnel says we're at 0.4, then if you roll the dice and it's above 0.4, then reflect, otherwise, or refract, otherwise reflect. And if your Fresnel says 0.98, then most of the time you're doing reflection and not refracting. So there's ways of enhancing the result without statistically changing the result. And if we combine more than one model, such as trying to get the rays to congregate more towards light sources versus sampling the BRDF, then if we put both of them together, then we can get a blend of quality from one versus the other. So multiple importance sampling is almost a given. If you're going to write one from a commercial one from scratch, you're going to probably do multiple importance sampling in order to get the results. Now, other approaches we talked about were radiosity. At the end, I want to talk about instant radiosity, but we're basically talking about light mapping and the radiosity equation. In other words, you have all these form factors and you have to calculate how much light is reflected. And the main method that's used is the Hemicube model. And with the Hemicube model, we can figure out the visibility a little bit better because we have fixed functions that we can evaluate. So it's a multi-pass, so you have to let it go for several iterations, normally until the change in intensity from one frame to the other is below some epsilon value. So you can see if we get to the third pass, it almost looks the same, but we have a lot of darkening in some of the areas that need more scattering to get back there. So that's a downside to radiosity. And the way that we do it, given our scene geometry and our materials, we can go ahead and subdivide the geometry into small patches, and then we just simulate light transport. Basically, it's heat transfer. That's what we're simulating between patches. And yeah, we need to filter, because if you have geometry that's masking other facets, and you get darker areas that you need to account for. So if we filter this, then we're getting pretty good, pretty close to a smooth out solution. And then we have to let it, like I said, we have to iterate. So you'll see many dark areas the first time around. And after 3, we're pretty close, but you can tell there's still a significant amount of light to be gathered as we let the radiosity algorithm continue. So one way to improve some of the quality issues with radiosity is to use adaptive subdivision. So the areas where shadows are more likely to have an edge, we'd want to subdivide in those areas, whereas areas that have less variation over the surface of the patch, then we can say, let's not subdivide that as much. Normally what you see is radiosity is used to create light mapping. And light mapping is basically a texture map in the scene that represents the global illumination solution for the scene. So it's good for static geometry. It's not very good for dynamic geometry, because you would have to recalculate a significant number of patches if you had an object going back and forth. In other words, a character walking through a corridor in a light mapping environment is not going to cast shadows on the wall. Like, they're not going to change the inner reflection of the wall. Now, they might cast a shadow on the wall, so you kind of hide that. Your eyes are distracted by the high detail stuff. All right. So the solution for dynamic objects is to use irradiance volumes, or pre-computed irradiance transfer. And so what we do is we store irradiance at different points in space, typically as a cube map, and then we can turn that into a spherical harmonics representation. And we said that spherical harmonics was a way of representing a complex function on a sphere, and a light probe matches that that constraint. So we have every direction we need to consider. And so what it allows us to do, though, mainly is to make an object look like it belongs in the scene. So we have the same brush metal material, but different irradiance volume surrounding it. So we basically treat the irradiance volume as infinitely far away, and then use that to light the 3D model. And the way that we do this is we have to calculate a visibility term from at each vertex that says how much of the irradiance volume then is visible from any given direction. So we use a spherical harmonic for that as well. And we took a look at that in one of the papers, I think, online. But the idea here is, so these are the spherical harmonics. And so we can approximate a more complicated function by simply assigning a numerical coefficient to each one of these and then adding them up together. So if these were our original functions, then these are various approximations of the original. And you notice that all the high frequency details are stripped away, but this is numerically equivalent, I guess, to this one if you were to, I guess, add them up. So with spherical harmonics, if the old model is basically use a flat constant value to represent ambient, the ambient lighting, and with spherical harmonics, we can say, well, more or less, this is what it is. And we basically solve the problem that if we had a light then coming in sideways into the scene, with regular point light shading, we would get huge dark areas where we know that that's not really the case. And so spherical harmonics really adds a realistic boost to our rasterized images. All right, so what they look like for a particular scene. So we can see a kind of a ground truth representation, a spherical harmonics representation, and then what the actual shape is. So this side of the building has got an opening, so we see a lot of light coming in from that direction. Okay, we can use path tracing to create an irradiance volume. And what this image shows here is that we don't necessarily need to have a high quality image either. We could just roughly get a solution and then use that. So spherical harmonics can smooth out a very noisy image, and we can use this low frequency then to light the objects inside of our scene. So the way to pick then the irradiance volumes, if they're all scattered around the scene, then we can do a Delaney triangulation. And for any point that we are interested in shading, we just pick the closest ones that are surrounding it, and we can interpolate the coefficients of the spherical harmonics together and use that then to light. So we're basically creating a gradient for the irradiance volume, and that allows us to dynamically light a complicated 3D model that also doesn't have issues associated with, or as many issues as just interpolating or extrapolating data. So this is how you might see light probes in Unity. And so this is just an example. I guess this is, in fact, how we do real-time global illumination inside of a video game. So now on the horizon, though, we have these really good rasterization techniques, but we'd also like to do ray tracing since we're getting computationally able to do that. So we have the 6 components. We can generate rays and some way of accelerating the ray to object intersections. Then we maybe possibly like to allow for procedural objects. And we've looked at procedural objects using sign distance functions that can be quite sophisticated. Otherwise, we can maybe come up with something for triangles. An any-hit shader can be used if we intersect any object along the path of the ray. And when we get to the end of that, if we have a hit, then we can call the closest hit shader, which can recursively call trace ray and repeat the process. So if you're doing shadow rays or something. And if you're doing triangles, then we would want to get barycentric coordinates and a triangle index. So we're going to talk about barycentric coordinates today. And so if we miss completely, then we want to use a miss shader to kind of decide how we're going to shade that pixel. All right, so this is where your sky rendering might come into play. All right, so here's just a quick short version. So we generally have ray generation, going through the acceleration structure, and then finally handling a hit at the end. So we're using the book Ray Tracing in One Weekend to write a brute force path tracer. And he covers everything from how do you just get started to getting behind the math of a serious ray tracer. In other words, introducing you to Monte Carlo integration. So this is the general pattern he follows in the book. And this is a simple sky mist shader we talked about earlier in the class. So we can blend from white to blue or from orange to blue. Depends if we're trying to get like a dawn kind of color scheme. And last time we spent time talking about ray marching using sign distance functions. And ray marching, so just to review this, you know, the easiest thing we could do is calculate a ray sphere intersection. So what we want to do is solve the ray equation, O. So we have the point equals O, the origin plus T times the direction. And we'd like to plug that into the equation for a sphere, which is P squared minus R squared equals 0. And so if we rewrite this, we can write it in terms of a quadratic equation, which then we can solve. So if we had AX squared plus BX plus C equals 0, then our A would be the direction squared. So B would equal 2 times the origin and the dot and the direction, and C would be O squared minus R squared. All right, and so we have 5 cases. Case number 1 is the ray is behind the object, and so we get 2 real solutions, T0 and T1. They're both greater than 0. We just pick the closest one. That is our closest hit. And then if they're both the same, that means that we're grazing the surface of the object. If our ray starts out in the middle, and this is a case where if you're ray tracing inside of a container of water, then you're starting inside the volume. And so if your T comes back less than 0, then you know that it's behind you. And if your T is greater than 0, you know it's ahead of you. So your closest hit would then be the second T that you get. If you get no solutions, in other words, you compare the discriminant, then if the discriminant's less than 0, you know that you have no intersection with the sphere. And the last case is that the object is behind you, so both your T values are less than 0. So let's see how to do this with sign distance functions. So if we were to take a look at the equation for a sphere, we can write this as a sign distance function simply by putting everything on one side. And I think that we'd actually want to take the square root of that. I think that's a typo. But the function is going to tell us whether we're inside or we're outside. So if we're inside, then we would expect the length of our point, if it's inside a unit sphere, to be less than 1. So if our r squared was 1, then we'd have a certain, say, this is how far inside we are. So it would be negative distance. And it's positive distance if we're outside. So we use the example of, if you want to test this out, you could just use cosine theta, sine theta for a circle. And you can test points in the circle and out of the circle or on the surface of the circle, and you will get negative values, 0 values, or positive values. So we can use this idea of a sine distance to determine then how much space can we then travel along the path of the ray before we potentially hit something. So this is a numerical method, so we have to iterate a certain number of steps, and we normally are checking we're waiting until our distance to the object is less than some epsilon value. So what we do is we calculate the point. So we origin plus t times direction, and then we plug that into the sine distance function. That gives us the distance that we can travel, and if it's less than the epsilon, then we are so close, we're going to go ahead and stop. Otherwise, we travel d distance along the path of the ray. And if we pass our t max, in other words, we get to the end of our objects, or we say we're only going to trace so much, then we return false. So to look at this graphically, we set our t min normally at the start of the ray, and we can calculate the sine distance. So over here, we know that if we were to use quadratic equation, we get 2 real solutions. If we use the sine distance function, then we get the value basically from here, from the edge of the, from the center of the, it's not to the center, but it's to the edge of the object. And we can say this is the amount of distance we can travel safely. So we go ahead and do that. And we check to see how far we are from the edge of the sphere. Now it's greater than our epsilon, so we can keep going along. So we keep traveling along the path of the ray. And this circle will keep getting smaller and smaller and smaller. If the ray was pointing straight at the middle of the sphere, we would basically jump here in 1 step and we'd be done. But there's a lot more steps at the edge. So as we get to that one case where we're at the corner or tangential to the surface, then we could be getting numbers that are smaller and smaller and smaller. And as we kind of tip that over, I guess you miss the object, then what'll happen is these spheres will get smaller, and then they'll start jumping up really big because your sine distance function is getting larger. And so before you know it, your ray a miss ray is typically going to be very quick. Okay. All right. So at this point, we have our intersection. So just to reiterate, ray marching, we're going to trace our path to 1. We basically march in these big steps until we get to our object. So some comparison code. So this is code if you want to do quadratic equation, and this is code with the superquadratic, or not, well, wrong function, but this is with a sphere. We got to fix that. And so the big issue though is that you can calculate a sphere in basically 1 step. Whereas with a ray marching, you have to do an iterative value. So there is some cost benefit there depending on what you're trying to do. So the way that we go through the objects, determine which one's closest, is we just compare our t values that we get out. So the first time we will hit object number 1, so we can safely say that our t max is no more than where we got our closest hit to object number 1. We go through the next object number 2. Object 2 is closer than object number 1, so we can update our t min and t max values. And when we get to object 3, we can see that 3 is outside of our range that we're looking for, so we don't even have to compute an intersection with 3. And this is a case where having the quadratic equation might be, you could simplify the scene in terms of, let's just do a test with a sphere and see if it's even worth going or not. And then you could use ray marching if the object is more complicated. But those are optimization techniques. So you have to use them when you need them. So the way this algorithm works is we're going to go through all the different items in the scene graph, and we'll set our Tmin to 0 and our Tmax to some large value, like 1,000,000 or something. And if a ray intersection occurs, then we'll call our any hit shader. And we'll check to see if it's outside our new Tmin and Tmax values, or our existing Tmin and Tmax values, and we'll mark the new ones. So we'll keep going until we're all done with objects. And so if we found an object, then we can call it closest hit shader, and this is where you do your most expensive calculations. Otherwise, we call a miss shader. What is the color if we don't get an intersection? So one of the most useful things that we can do is ray trace triangles. And but ray tracing triangles is not exactly the easiest thing to do because of the math. So we're going to talk about the math for a little bit. So August Ferdinand Mobius introduced this technique of barycentric coordinates. And the idea here is, how can we locate a point inside a simplex? A simplex in the two-dimensional case is a triangle. In a three-dimensional case, it's a tetrahedron, and there are higher dimensional orders of a simplex, all right? So we would call it like a 3-simplex or a 4-simplex, talking about higher order ones. But the idea is that you can't represent space in any more fundamental unit as that one. So in 3D, we'd have tetrahedrons, and so going back to the discussion of pre-computed radiance transfer, that Delaney triangulation is computing simplexes. So for any point in space, we'd have 4 spherical harmonics we would want to interpolate and find the middle of. So let's consider a triangle T, and it has 3 coordinates, so R1, R2, and R3. Although we're going to stick to the alphabet here for the most part, so A, B, and C. But depending on where you read, I just wanted to just show you, this is the Wikipedia information. So if you're on Wikipedia, you're going to see R1, R2, R3. And so then any point R can be represented by a convex combination of R1, R2, and R3. A convex combination means that these coefficients, lambda 1, lambda 2, and lambda 3, when we add them together, it's equal to 1, and all of them are greater than or equal to 0. Okay, so we add them together, we get 1. All 3 of them are all greater than or equal to 0. And then we can calculate the point inside of T by simply using these lambda values and multiplying it with the points. So this is a this is a handy way of being able to determine where are you inside of the triangle. So if so you'll find alpha, beta, and gamma in the literature. You'll find U, V, and W also in the literature. So they're all talking about the same thing. So for simplicity, I'm going to use U, V, and W. It's easier on the eyes. In order to calculate barycentric coordinates, right? So we'll restate our formula here that any point inside this triangle ABC can be calculated by the product of, this is like the dot product, right? You just look at it. Well, it's not a dot product. What you have is the dot product of a point in space, but it's more like a vector from the origin to the point in space, okay? So we have the sum of these 3 coordinates, and they're real numbers, right? So they add up to 1. And if you know 2 of them, you can always get to the other one, because if the equation is U plus V plus W equal 1, and we don't know W, we could just solve the equation in terms of W, and now we can find out W. And that means that U plus V is also less than or equal to 1. So we know that this equals 1, but U plus V has to be less than or equal to 1. And the point is going to be inside the triangle if for every U, V, and W, they're all within 0 to 1. So if you have 1 negative value, you are not inside the triangle. That's the idea there. So now, in order to get these barycentric coordinates, right, that's the next question. We know what they are. We know how we can calculate the point inside of it. But how do you actually get those values? Well, the way to get them is to calculate the dot product between two of the edges. All right. So in order to get the area of a triangle, and we have the edges A, B, and C, or AC, AB, and BC. Those are our edges. We can evaluate this formula that the length of B minus A times the length of C minus A times the sine of theta over 2. That is the area of the triangle. All right. So we divide by 2 because what we're doing is we are calculating half of the parallelogram. So technically, the top part of the numerator for this equation is calculating the area of this parallelogram. Okay. And we can see that B minus A is just simply the edge. So that's edge number 1. And C minus A is edge number 2. And so we multiply the length of this one times the length of this one. All right. And so that's basically length of this times length of that. We divide that by 2, but we also have to multiply by sine theta because that's going to cause our area to decrease. So go back to our mathematics. What special tool can we use if we want to calculate the sine of theta?
Cross product, but maybe we want over.
So yes, it's going to be the cross product. There's no special, we don't have to actually do anything special here. The cross product is what we're going to do. And then we just take the length of the cross product between these two edges and divide that by 2. So when we find the length, what is the definition of the length of a vector?
Geometric average.
No, not quite. It's the length of the component, right? So when we take the cross product, what we're saying is give me a perpendicular vector from AC and AB. So this is the normal, right? This is the normal. And but this is not a unit length normal. This is the full size normal for the triangle. And so what the product that you get out is it's called the triple scalar product. What's cool about this particular product, and this is why I talked a little bit about geometric algebra, is it's got the concept of let's see if they have the geometric thing here, right? So we have A, B, and C, and these form a parallelepiped. But the triple scalar product is defined as A dot B cross C. So when we do this is the signed volume of the parallelepiped, okay? Whereas the cross product is going to represent the signed area for the base of the parallelepiped, okay? So when we looked at the triple scalar product, this gives us the volume. We take the triple, we take the cross product and we get the area, okay? Very, very neat. It feels mysterious in a way, but there's a geometric interpretation that when you take, so in other words, when you take, when you take a cross product between two vectors, it represents the area of this parallelogram that's created when you join those two edges together. So if the cross product of two normal vectors, right? Cross product of two normal vectors, what is the area then of that parallelogram? So let's cheat and look at this equation, right? And given that we're dividing 2 because it's 2, if you have 2 normal vectors and you take the cross product between the 2 of them, what is the area then of this parallelogram? That's going to be sine theta. So if you have 2 normal vectors, they both have a length of 1.
Oh.
Right?
Yeah.
The length of vector 1, right? The length of vector 1 is 1, and the length of vector 1 is 2 is 1. Then they basically cancel each other out. And so the area then of this parallelogram is sine theta. Pretty cool property. So if you know you have 2 normal vectors and you want to find sine theta between the 2 of them, you just take the cross product and get the length. Pretty easy. Or another approach is to take the dot product between the 2. You get cosine theta, and then you can just take advantage of 1 minus cosine squared theta equals sine theta. Okay, so that's how we get the area of a triangle. So this is important to understand. Take edge 1, edge 2, you take the cross product and you take the length. That gives you sine, that gives you the area of the parallelogram. We divide by 2 to get the length of the triangle. So now we want to calculate the barycentric coordinates. So if we kind of think of u plus v plus w equals 1, what we're saying then is that u is going to be equal, it's kind of cool, u is going to be equal to the area of this smaller triangle divided by the whole area of the triangle. So if you have u plus v plus 1, w equals 1, that makes sense because you divide the area into 3 different pieces, it should equal 1. So what happens is that as u gets close, let's say 0, u is getting closer and closer to 0. That means v and w are both getting bigger until eventually u is on the edge. So then if u is on the other side, what is going to happen to that value?
0.
It's going to be negative.
Yeah.
You get negative area.
Oh.
So as we're going, so this is u is positive. We're moving u closer and closer and closer to the edge. It's getting smaller and smaller and smaller because the area, right? Area is getting smaller and smaller and smaller. As soon as we peek out over here, u is going to be negative, right? Because the area is outside of this triangle. That's how you know if you're outside the triangle. So you're inside the triangle if they're all positive. In other words, they all represent their own piece of the pie, right? Their own piece of the triangle. So in order for us to calculate, we would basically divide the area for, say, C, A, and P, right? So that's U. And if we want to get B, we divide the area, so A, P, and B. And then lastly, to get W, we would need the triangle C, P, and B, right? Or BCP. And that's how we calculate the barycentric coordinates. All right, so these are all things we know how to do now because we know how to calculate cross product, we know how to calculate length. And so the next thing we want to do is be able to use them. So the first thing is we can calculate the normal simply by, and in this case, we are not talking about the unit normal, we're talking about the vector, the unscaled vector, right? The cross product of AC and AB. So we take that, and obviously that's going to point in the same direction as the unit normal, but it's going to have length associated with it. So then we can basically calculate the area by just saying 1/2 times the normal. Okay, so if you have the original vertices, you want to calculate the area of the triangle, then it's 1/2 times the length of the normal. Now, question is, should we normalize n at this point? Should we normalize n? And it's an important question to be able to answer because we've been talking about normalizing n every time we do it, right? N dot L lighting. We have to have a normalized n. But in this case, do we want to normalize it? No. Well, why is that? We want to know if the area is going to be negative. Exactly. Okay, so we're going to take a look at two edges. In order to calculate then the value for u, what we can do is we're going to calculate a vector v. And this v basically equals, so for this one, it's c to b and p to b, right? So we have two vectors here. I apologize because these are not, they don't match up 100%. I have to fix the diagrams. But the point here is that we take the area of the smaller triangle and divide it by the area of the bigger triangle. So we're just doing the exact same thing as before. Now we want to check to see if the point we're interested in is on the right side or the left side. So it's on the right side if n dot v is less than 0. So if we take our normal and we take our perpendicular vector over here, right? And we're going to take the dot product between the two. Then as it's getting closer and closer to 0, what does n dot v equals 0 mean? What does dot product mean?
The determinant vector that it's going with. If it is transposed onto the main vector.
Yeah, there's some of that, but what the simpler answer? What does dot product represent? Gives us the cosine, right? And so we're interested in the sine of the cosine. So what does it mean when cosine? So we have three cases. Cosine is greater than 0, cosine is less than 0, cosine is equal to 0. What does cosine equal to 0 mean? It's the same vector. The point, the same direction. Okay. Secondly, if it's less than 0, it means that it's pointing away from, they're pointing away from each other in the opposite direction. This, you would get it, for instance, if I was taking the dot product of a normal on this table with a light source that was above the table, I would always get a positive cosine. As the light goes down and it starts to go underneath the table, I will now get a negative cosine because the angle is greater than, or it's less than 0, right? So cosine is giving you positive 90 degrees to negative 90 degrees. That's the idea. So if I take the dot product then of v, right? This is the vector going from my point, and I compare it with the normal, then what's going to happen then is as those start to go, you know, as they get similar, so you would expect this to be 0 on the edge. So if P was close to the edge, it would be 0. And then as it starts speaking to the other side, then we're going to get a negative cosine. All right. So it kind of represents the angle as you're going out, Okay. Then we do the same test with edge number 2. So we calculate the area, and that's V. And then we go ahead and test to see if P is on the right side. So we do the same test, n dot V is less than 0. So that is how we use it to determine whether the point we're interested in is inside or outside of the, so it's just a slightly different way of looking at it from the previous slide. Where it comes into interest, though, is if we want to shade with these barycentric coordinates. All right, so let's just say we have a triangle with 3 vertex attributes. We can use barycentric coordinates to interpolate them. So, for example, if we had colors like this triangle, maybe it's blue, green, and red, and we want to interpolate, we want to find out for this point inside the triangle, what is the color? So if we have our barycentric coordinates, u, v, and w, then we can calculate exactly what the average, what the color we should pick. It'll blend the 3 vertex coordinates together. So in this way, we can we can figure out exactly what the color ought to be. Texture coordinates. Let's say we want to put a brick texture on here. Well, we need S and T. SNTR coordinates to look up in a texture map. So we have 3 texture map coordinates at each of the vertices. So if we want to find out the actual texture coordinate to use, then we will say, let's take our UVW barycentric coordinates and blend then the 3 texture coordinates. And that will allow us to figure out what texture coordinate then do I need to look up in order to render a texture map on this triangle. All right, any questions so far? Is this cool? It is cool. The power of linear algebra. Although you would never learn this in linear algebra class. You should take linear algebra, but you will never learn this in linear algebra class. We haven't talked about how do we get the intersection though, right? We've talked about how you can use barycentric coordinates to come up with the point inside the actual 3D location. We talked about how you use barycentric coordinates to calculate the material property for that point in the. We talked about finding out whether or not a point is inside or outside. We haven't talked about how do you get a ray to determine whether or not it's going to hit it or not. So we define our ray as an origin and a direction such that we can calculate any point by saying P equals O plus T times D. And we'll use we'll continue using A, B, and C as the 3 vertices. So one of the first checks we can do is check to see if the ray is almost parallel with the triangle. So if you have a ray that's, you have your polygon and you have a ray that's basically traveling almost parallel, it is very difficult for that ray to even hit it. All right. So we're basically going to say if the absolute value or the magnitude of n dot d is less than some epsilon, then return false. So if they're almost parallel, and the problem here with parallel stuff is then you start getting areas that are equal to 0, and then you start dividing by 0, and then you get not a numbers. And there's nothing worse than troubleshooting not a number in your shader code. So we use this as a way of like, okay, let's get out of here if this is going to cause us problems. The next thing to do is to calculate the distance from the ray to the triangle. So the way that we do this is we can calculate our normal dot product with the point A. So we can just pick one of the points, and we'd like to just find out what the distance is from, how far does the ray have to travel in order to get to point A. So what'll happen there then is we can calculate, I think actually what this means is that since A is the point in space and N is the normal, it has something to do with everything kind of points from the normal, okay? But the idea here is we can calculate the distance here, and then we can calculate T by calculating N dot, the dot product of the normal and the origin plus the normal times the point A divided by the the magnitude of the normal dot product with D, the absolute value. So what we want is absolute value. So that's what that is, absolute value of N dot D. So we're going to use that same calculation here, but we want absolute value here so that we're always looking at positive distance. So this basically has the effect of dividing by the cosine of the normal versus the direction, okay? So because if the normal and the direction are going the same way, then what is N dot D going to be? 2 vectors, almost exactly the same. What's the dot product? Cosine of 0 is, yeah, and cosine of 90 is 0. So if the normal, right, sticking out this way and we're traveling parallel, then we're almost at 90 degrees. That means if we get down here, we're dividing by 0, okay? Now, if T is less than 0, then we're behind the triangle. In other words, just like the sphere, right? it means the ray starts at, because we're trying to calculate where is the intersection between the plane of the triangle and so that's either going to be behind or it's going to be forward. All right, so we're basically applying the equation of a plane to this problem. So t less than 0, that means that the triangle is behind the ray. So yeah, we don't have an intersection. So now that we know that we're in front of the ray, then we'll compute P equals O plus T times D. So we're projecting the ray. We're trying to say where on the plane for this triangle does it hit? And then once we have that point, then we're going to use that to test against the barycentric coordinates. So now we want to evaluate the inside-outside test to calculate U and V. So for edge number 0, we have 3 edges. We got to test each edge. First, we calculate the first vector. And so if P is on the right side, then n dot V will be less than 0, and we return false. So if we're outside the first edge, then we're done. Edge 1 and edge 2 are different cases because we're trying to calculate U and V. So just like before, you'll notice that the equations change just a little bit, and there's a reason for that. And the main reason for that is we can do some math, and the Scratch a Pixel website has some more explanation of what we're doing here. But if you were to take a closer look at these equations, then there's some simplifications we can make. So if you expand all this out, you'll find out that what we're actually doing here is dividing by the normal dot the normal. Okay. And so then what we can do is we can just say, let's set U equal to n dot V. Test if n dot V is less than 0, because the cosine is going to make it positive or negative. So we don't need to divide at this step. And so then we take edge number 2, calculate V equal n dot V, and then if it's less than 0. So then what we can do at the very end, then we can divide by the area of the, so this is 2 times the area of the parallelogram, right? That's what n dot n represents, area of the triangle, or twice or half the area of the, it represents area of twice the triangle. So. All right, so that's how we do the inside-outside test. So this tells us if we're all less than 0, then we can return false. And there's a reason why we do this. We have all 3 edges here, because what we can do then is basically stick everything inside of a single vector 3, and then you can do there's some parallelization that you can get, optimization here. Okay. Any questions on barycentric coordinates? All right, they're still mysterious. I hope that today we can talk a little bit how to use them. But this is if you want to add triangles, which I'm sure many people do. So let's look at how we would do a scene graph in GLSL. So at this point, I'm going to assume that we're going to implement a path tracer or a ray tracer in GLSL. So it's always helpful to kind of get some experience there. So if you're going to do that, and this applies to C++ as well, right? We're just going to apply raw ray tracing. So we need to have a number of hittable objects. So we'll start out by having 0, and then every time we want to add a new object that can be hit, then we just add it to this data structure and then increase the hittable count by 1. And this is, when you're compiling shaders, the compiler has to be able to make certain assertions about them. So in other words, we use constants in order to make sure that it knows how many times it can unroll a loop, for instance, or it knows definitely where in memory it needs to get a piece of, if it can't calculate that, your shaders oftentimes won't compile. And you'll be like, but I can do this in C, or I can do this in C++. And the problem is that the shaders are running on such a limited core that branching is often not something you can do very easily, or dereferencing memory is expensive. So, so we actually have this, this pattern happens a lot. So over here, we're adding hittable. So we check to see if the count is greater than our maximum. So that's something we can calculate easily. And then we have to loop through our hittable structure and until we find the right one that's empty. So if this was regular C, we'd say, well, yeah, just, you know, access hitables wherever hittable count -1, but you can't do that in shader. So we have to literally go through every item and stop then at the item we want, and then we can update. So this is maybe you've seen this already in your own code. I don't know if you have or not, but this is this when I first started doing it, I was like, why isn't this working? And so I had to spend time debugging all that. So just know that if you have an array and you want to iterate through the array, you have to basically manual, and you want like element I, you have to iterate through all the elements until you stop at the one you want. If it's a good shader compiler, it'll optimize that away. It recognizes stuff like that because these are like common techniques. All right, so we have a way of creating, so we want to create a scene. So we have a function to kind of add a data structure to our list. And so it kind of looks something like this, where we might say create a torus, right? We have a function that creates a torus. So we'll create a hittable and initialize the properties and then return it. So it's like a factory function. And then when we create our scene, this function basically says, okay, let's add a torus or let's add a sphere and give it these material properties. All right. So the dot dot dots mean that's up to you to specify what information it's going to have. So once we have a way of representing the scene as an array, and we have a way of adding several objects to it, then we can go ahead and trace the array. And so this pattern over here is basically following the real-time ray tracing pattern. So the acceleration structure is basically we have no acceleration structure. We just go through all the items in the list, brute force, and then do it. But if you had a good acceleration structure, it might be like a binary tree or something, you say, or an octree, you say, am I on this side of the plane or this side of the plane? Then you decide you can get that logarithmic selection to find this set of objects that you can hit and so on. All right, so over here I set my Tmin and Tmax to a minimum and a maximum value. And this is another case of, okay, if I is greater than or equal to hittable count, then break. So it has to know how many times this for loop is going to loop. So we have to put a constant here. So I would like to say just I equals 0, I is less than hittable count, but I can't do that. I have to give it a constant, and then I stop when I hit my limit. So over here is when you can call your intersection shader. And so we'll pass it our hittables object, our ray, our Tmin and Tmax, and the hit record. All right, a hit record is going to be used to store things like here's the current color or here's the current normal. And if our intersection shader succeeds, in other words, we got an intersection, then we can update the hit. Right, we start off with -1. In other words, we don't have an object. And then we set our Tmin equal to the new T. So we only start tracing. We're looking basically for objects that are before Tmin. Otherwise, we call our any hit shader. And so we can use that for different kinds of things like it might be shadow rays or participating media. We might have some reasons for that. So after we get to the end of tracing the ray through the entire scene, and so normally this hit record, you want to keep track of like color and all this other stuff because it's expensive to kind of get that hittables object back out. Otherwise, we call the miss shader. So this kind of follows what we've been talking about the whole time. All right. So that's the general format there. One of the things we haven't talked about then is, well, how do you move objects around in space? So we talked about signed distance functions last time, but we were coming from they're all, the assumption is that they're all at the origin. So that's an assumption that signed distance functions have. So then how do you move like a sphere from being in the center of the scene to somewhere else in space? So the key there is we have to transform the point that we're testing so that it is in this new coordinate space. So we're basically trying to move whatever the current world space coordinate is into the local coordinate space of the object. All right. So in order to do rotation and translation, the key to remember here is you have to use the inverse matrix, right? Inverse matrix takes you from one space to another. So if I had, so if that blue chair right there has a matrix that takes it to world space, in order for me to move from world space to the location of that chair, I have to multiply my world matrix by the inverse matrix of that chair, and that will move me into the space of that chair. So if we have a rotation matrix, which if you remember, the inverse of rotation matrix is what operation can you do on a rotation matrix to get its inverse? Transpose. Take the transpose. That's very easy to do. Take the transpose of a rotation matrix, it's its own inverse. All right. And you can prove that if you just start out with a simple rotation. So you have cosine theta, sine theta, minus sine theta, cosine theta. If you take the inverse and you multiply it, then you end up getting these like cosine squared and sine squared. And then you know that you're going to end up getting the identity matrix. All right. So what's the inverse of a translation matrix? For a translation matrix? Inverse of a translation matrix. So what does a translation matrix do? Okay, so if you were to do the inverse operation, what would you do? Okay, multiply by -1. You subtract the location. So if I moved myself 5 spaces forward in the X direction, I have to move 5 spaces back. That moves me back, okay? So what we can do is we can then transpose the rotation matrix to get the inverse, multiply by P, and then subtract the translation in order to calculate the inverse, right? If this was a 4x4 matrix, then you could just take the inverse of that whole matrix and multiply it by P. But since we're using a vec3 here, we'd have like a 4x3 matrix, and that wouldn't work. We can't just calculate an inverse of a non-square matrix. All right. So this is our quick trick to doing it. So what we're ultimately doing here is calculating the inverse matrix of this rotation and translation matrix. But we do that by separating it out. And we take advantage of the fact that a rotation and a translation matrix, we've done this exercise before. The top left 3x3 matrix is the rotation matrix, and the fourth column is the translation. And the bottom row of a 4x4 is just 0, 0, 0, 1. So we can drop that off. It never changes. Scaling is a little bit different. The reason why rotation and translation works is because it doesn't compress space. So if I were to rotate and then move, all my angles are preserved, all my lengths are preserved. There's no issue there. But scaling, we're squashing or expanding space. So it doesn't work that way. So what we can do for scaling then is we can multiply our point P times our scaling factor. And then when the sine distance function comes back out, we can divide by the scaling factor. Because the sine distance function, right, it's giving us the actual space we can travel along the ray. So if we scale down the point, it gives us the distance, and then we can divide out, we can scale it back up. All right, so that's why scaling works. I include this last one, symmetry, because it can be useful for creating more than one object, right? So in this case, what you would do is you would take the absolute value of the component that you want. So if you wanted to mirror it on the x-axis, you take absolute value of p dot x. So it's going to have the effect of using the x-plane as a mirror. So you can go back and forth. You could also do the same thing with some of the other ones, like say the xz or coordinates or so on, if you're trying to get one quadrant. We talked a little bit about constructive solid geometry. That's creating composite objects out of the other ones. So this is more or less how you start to move things around in your scene. This next one is how do you construct more complicated objects? So if we have union, we can take the minimum of distance 1 and distance 2. And this has the effect of giving us the closer object, right? So for instance, if I was on this side, the ray's coming down, then the minimum value is the sphere, right? We're closest from the sphere. But coming from the other side, we're closest to the rectangle. So that is how the minimum works, right? Subtraction. Yeah, so we want to subtract one object from another. So what we can do is then we can take the max of minus distance 1 and positive distance 2. Last time we mentioned why that was the case. What happens when you take the negative of one of the distances? If the sign distance function returns the opposite values, what does that mean? Yeah, so yeah, if your distance is negative, right, before, then your distance is positive. So if you're inside, it feels like you're inside the object. Well, your ray's never going to get out of the object, so it won't work out that way. And if you're outside the object, it's going to be like you're inside the object, and so then you don't get anywhere either. So subtraction is basically you flip the sign of the one you want to subtract. Intersection is the maximum of the two. So when you do intersection, then you basically only get the area or the volume where both objects are together. Now there has been some work to make these work in a smooth way. So in this image, we have a hard union, subtraction, or intersection, but smooth kind of works a little bit like blobs, right? We haven't really talked about blobs, but they work in a similar method. And the idea here is that we're going to blend as the sign distance functions get closer and closer together, we blend between the two so that, and we can see that here. So like for union, we're going to use clamp. Clamp is like one of those just really useful functions, but we're say 1/2 plus 1/2 times distance 2 minus distance 1 divided by k is going to be our new, this is our mixed value. And so if k is equal to, you can use k to adjust how smooth that joint is going to be, all right? So well, basically what that means is that if h is then 1, then we're going to get distance 1. And so what we're trying to do is just figure out, it's a like specialized function to kind of decide, well, which one should we then use? All right, so we're actually using both, but it's one of the things you have to kind of try out. So that's how you do smooth functions, which is nice because you can create more organic shapes that way. Repetition. So if we wanted to repeat ourselves, and like, for example, the grass blades here, we can use the modulus operator. So let's just think integers here. What do we use modulus for in computer science?
The
remainder, right? So if you're taking the modulus of 8 and you're counting integers up, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, you get a repeating pattern, even if your number is like 120, whatever. So what we do here is we can take our point P and we have a vector C. This basically says, how often are we going to repeat? So this gives us kind of a dimension for that. And we just take the, we take our point P, add half of this, this box, and then modulus it with the box. So what will happen is that we'll get this infinite repeating pattern if we do this, all right? If we wanted to repeat only a certain number of times, then we can pass in another vector that kind of says, okay, how far, what's the constraints of this area or volume that we're in? And so if we take P minus, we can use this round function basically to kind of get it to repeat a certain number of times. So if we want to create this 3 by 3 block, then we can use this function. And this is useful if you're trying to create some complicated objects. So I can tell from looking at this, they probably used a mirror, they probably used a symmetrical operator between this mushroom and this mushroom. They obviously use repetition for these plants, okay? Because they're more or less, they look the same. All right, but there's one more key, and that is, and I'm not going to get too much in detail here today, but you can do displacement. So if you had a torus here, displacement would move all the points out by a certain amount. So you could use a mathematical function to kind of add some variation to your shape. The other kind is to use twist. So you can take this sphere and you could like wrap it around itself as if you were twisting a piece of Play-Doh. And then there's bend, which allows you to take a shape and like bend it sideways. So if we look over here, we can see they probably used bend on the mushroom. They probably use some function to modulate the depth. They probably use the same kind of idea over here with these grass blades. So if you were to study the source code, you'd probably see a lot of these ideas. All right. Let's get into how do you make a movable camera. So we talked about barycentric coordinates. So we're going to ray trace triangles. Talked about how you might represent all the objects inside of the scene. And we talked about all moving different objects around inside the scene. So the question now is, how can we get a camera then that we can aim wherever we want it to? And so we know how to do that with rasterization. We use the look at matrix. And with a look at matrix, we have the field of view. So that's how far open vertically normally that the camera is open. So if we want a camera that opens 45 degrees or 90 degrees, then that's what we're talking about here, field of view. So we might call the vertical axis Y and the horizontal axis minus Z. So in other words, we're casting rays towards the user, right? So if we have a right-handed coordinate system, X, Y, Z points towards the user. So minus Z points us into the scene. Now, if we were to draw out the field of view here, and we were to take the tangent of theta over 2, then we would get the height of the, we get half the height using this one. And so we could use the half height then to calculate the width by using the aspect ratio. So we calculate aspect ratio as width over height, and then we can multiply aspect ratio times height, and that has an effect of giving us what should the field of view then be for the horizontal axis. So if you have a square image, this won't make a difference, but we typically avoid square images because debugging this is very difficult. So given a view angle and an aspect ratio, we want to calculate 3 vectors. All right. We're also given 2 points. So the location the camera is at and the location the camera is pointing to, and often an up vector that says, what do we consider up to be? And the reason why is because first we need to calculate W, and W is going to be the Z axis, right? So if we have from minus 2, then we're going to get a vector pointing from the camera into the scene. Then we're going to calculate U, which is the x-axis, by taking the cross product of what we think up is cross W. So in other words, if I have my camera and it's pointing as we're pointing it down, right? Pointing it down, then we have an up vector going straight up. So if I were to take the cross product of this vector going up and the direction that this is going, then we get an x-axis that is perpendicular to our view axis. Last step is now we need to actually get our vertical axis. And so we get that by taking our W matrix, so that's forward, and our X, and now we have an actual, that's how we get our orthogonal system for the camera. When do you think this is going to break down? When you look straight up or straight down, because then the sign between the two angles is 0, and you take a cross product and you get a 0 vector out. That's kind of useless. All right. So sometimes what you do is you maintain that up vector, and if you're moving slowly, then you can basically, or you just make sure you never look up or down. That's typically the common thing. All right, so we have our half window width, half height. Now we need to set the lower left coordinates of the window. So if we want to be able to view the scene to the left of the, so negative x-axis or negative y-axis, we need to be able to attach an offset such that when we go from the lower left to the upper right, we can use 2 coordinates, s and t, going from 0 to 1, then to represent any pixel on the screen. So we initialize the lower left as -w and -h. We don't need anything for z. And then the ray origin is just going to be the look from camera position. So that's where the camera is located. And now in order to get our direction, so we have S and T that we're going to map for, S and T we're mapping for the screen. So then we can basically use S as saying how much should we add for the U direction, right, which we calculated here. And T will say how much do we go up in the up direction. So when we add that with the lower left, then we will get the ray direction. And then we'll subtract the origin in order to get the direction the camera should be looking at. All right. So it's not too difficult, but you do have to understand the look-at matrix. So that's why we've had some examples of, you need to understand your tools, right? And having the look-at matrix is one way of being able to now we can point our camera anywhere we want in the scene. Okay. Any questions so far?
Trying to figure out how you get to each ray direction is centered on each pixel. Where's the translation between each of those ray directions with the camera's direction? Is that all encompassed in that last line?
Yes. Okay. Let's think about this. Let's hypothetically say that U is the direction pointing in the x-axis, V is the direction pointing in the y-axis. What will happen over here? So let's ignore U and V because they're going to be unit vectors. All right, so that's one thing. These W, U, and V are all unit vectors. The lower left, if we start at the lower left, and let's just ignore U and V for right now and -O. If we have lower left and S is 0, then we're going to get the coordinates from the bottom left, right, and the top right. And when we subtract, so that makes sure that we can get an actual like physical area in front of the camera, okay? Now, when we subtract the origin, what we're doing then is saying that ray in space, which is technically at the origin, okay? So maybe I'll pop this screen up over here. That is the left projection. All right. So we have the ray direction. So this is the y-axis, z-axis, Come on back. Oh, no. X, Y, Z. The look to direction where we start out is normally 0. That's the origin, right? So that's our P2 equals O. And so our camera is normally backed up here somewhere, right? So our camera, I'm just going to try and draw something. So our camera is looking along the z-axis towards the origin.
Yes.
Okay. So what we're going to do here with a P lower left, so our is we're going to then draw. This is where the pixels are.
Yes.
All right. So this is lower left. So this is basically minus W, and this is positive W, and this is positive H, and down here is negative H. All right.
Okay. Okay.
Okay. So what we're doing here by then using S and T, because S and T 0, so S and T are both in the range 0 to 1. S representing the horizontal. So as S goes from 0 to 1, then we are going to basically pick the actual 3D position on this image plane. Okay?
Yep. And then making a vector from the origin of the camera to that.
Right, because we're subtracting it. We're subtracting this from this. That gets us the direction then that our ray is going through the scene.
I'm getting that. The part that I'm missing is when you start moving the camera, how does all of the translations follow so that all your rays are
Okay, yes. So this is where U and V come from.
okay?
U and V come from. So let's see here. Do I have an eraser? Got some cloth. All right. So here's what's happening with the camera. So we'll just take a side snapshot. All right. So we know how the rays are going to go through the image plane from the camera. Perfect. Let's take a look at this view from the camera to the image plane. Okay. So this one has a direction. This is V. And this is W, right? And an X is kind of coming off here to, this is U, this is U, all right? So our equation then for, say, T, right? So this is T, and so this is T equals 1, and this is, say, T equals 0. So what we're going to do in order to calculate the horizontal or the y coordinate is we have T times 2H times T. So we want a vector. Right now, if we have T equals 0, we'll end up getting a point down here. For T equals 1, we get a point up here. But it's going to be along the direction for V. So if the camera is stationary and we haven't moved the camera, V is pointing up. V is 0, 1, 0, right? So if we calculate though, so let's say we want to tilt the camera. If we tilt the camera, so part of the look at matrix is going to calculate our new vector. So if our camera then is facing down, then we have V, we have U, we have W. What's going to happen then is that instead of getting, right, because 2T times 2HV, in other words, our T value is going to be going along the direction for V. So instead of getting this image plane, we're going to get an image plane that's right in front.
Right.
Right.
And the V would become 0, like 0.5, 0.5.
Right.
And then multiplies that by. Okay.
So the main thing here is that this is different now. We basically rotated the image plane around the origin so that it's parallel with the camera. So now when we subtract this point from this point, you can see that my vector then is correct. Whereas if the camera was rotated this way, I would get from here to here. All right? That makes sense?
Makes sense.
All right, that's what's happening. So this, that's why we calculate the UVW. That gives us the basis for this camera. And then we can transform then our image plane. So actually say this is where the image plane is located in 3D space. And we shoot the rays literally through that rectangle in 3D space. So if the camera's looking down, the image plane is projected as facing down.
Yeah.
If we rotate to the side, then the image plane is rotated to the side. And that's how we get those directions.
It takes a bit to internalize.
Well, the only way to internalize it is to code it up. Code it up and throw in some values and see what happens. Because you'll learn a lot more from seeing it slowly turn and you visualize the axes and you calculate these points as well, and you'll see that the whole thing is rotating together. So then we can easily calculate our ray directions as in where they actually are on the image plane to the camera. Then the next step is to handle the case where you have an aperture opening, in which case you don't actually have a position.
Right, you have an area.
You have an area. You have what's called, circle of confusion. So what you'd have to do is calculate random points on the disk every time you shoot a ray. And so what will happen is that then your rays will go, so I guess going from this example, if you have a ray going here and it'll go this direction, or that's going that direction, this one will go this direction. And I guess cumulatively on the whole camera side, there'll be like one, that's how you get the, blurred background or foreground, because at some point inside the scene, there'll be an area that's in focus, and as you get away from there, they'll get out of focus. So that's distributed ray tracing, by the way, is then, I can say, well, give me a large aperture. The more uncertainty you get, the more blur you get. The other approach, kind of going along with that, you want to do anti-aliasing. So what you could do then, if you had a pinhole camera, is everything starts here, but instead of hitting just this point, you calculate, let's just blow this up here.
Use subpixel.
You can do subpixels.
Yeah.
And either you randomly sample like here, 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 and then you can calculate those rays for each one of those, and then you take the average when you're done there. So that's how you do subsampling and do anti-aliasing. So yeah, there's basically two ways. So if you're doing both circle of confusion and super sampling, then you can have anti-aliased depth of field images. So you have to kind of put random numbers on both sides, or you can have a pattern that you're following. Good questions. Anything else? All right. Everybody feel like I delivered all the material I promised? I feel like sometimes I'll say, oh, we'll look at this next time, and we never do. But just from your own perspective on rendering. Okay, so let's, just as a way of I have to go back to one of the previous 801. All right, so kind of like where we are, where we're going. So we've kind of talked about ray tracing and global illumination. We've talked about OpenGL pipeline. So kind of the last things that we're going into are more shading and procedural generation and stuff like that. So I believe next week we're going to spend some time talking about how do you do all these extra fun techniques. But I'm all ears if you have something you'd like me to cover specifically.
Any idea how denoising works? The basic introduction.
Okay, denoising. In fact, I'll add that on here. Okay. Denoising. About you, Curtis, what do you think you'd like to cover in more detail? Especially stuff that might be helpful for your projects too, that would also be. Okay. No, well, I think it would definitely make sense to look at barycentric coordinates and how you use them for the material part. So I think that would be great to pair along with texture maps, because we talked about how texture filtering and stuff works, but we haven't really talked about how to use them aside from just sticking a decal of a picture on something. So, which there's some fun stuff you could do, like encode the shininess of the object inside the texture map. So you have some parts that are shiny and some parts that aren't. So there's definitely some nice things you can do with the texture map that you cannot do with just a plain texture, or procedural texturing, you know, noise, applying noise, stuff like that. All right. If you have any other ideas, post them in the chat, the CS484 channel. All right. I think my voice is done, so I'm gonna call it quits.